Our topic for today is just to introduce to us the concept of metals and their properties. And before we go, let us try to look at some linear objectives. So at the end of today's lecture, we don't have much to say. We just want, it is expected that every student should be able to identify some of the chemical properties of metal. We have known some before, but at least we need to understand more in order to know behavior of compounds. And again, we should be able to explain what is called reactivity series. Reactivity series, as you are going to know later, it has some applications which we need to know also. But before we know the applications, we need to get the concept straight. So before we go, I believe we have come into contact with periodic table. If I'm not mistaken, I think it was around lecture 5 or 6 when we were talking about periodic table. During that time, we said every element that is at the left side of this zigzag red lines, they are all metals. So if we look at all the 118 elements or 103 elements that we have here now, we are going to see that if you just carve out this place, we're going to see that we have more metals than non-metals. So invariably, what I'm trying to say is this: we have more metals than non-metals. In fact, almost 80% of elements we have currently now, they are made of metals. You see the group 1, the group 2, or the transition elements, the actinide and lanthanide series. All these ones here, it is only from here that we have it. So in terms of number, we have more elements that are metals. So that is why we need to study them. That is one of the reasons. Another reason is that apart from the numbers, in the quantity, we still have more metals than non-metals. That is the second reason. The third reason is this: as we're going to see now, majority of elements, they are the things that we use daily at home. So there is it's imperative that we study them in order to know how each of them behave and the condition to which they can be subjected to, so that it will be useful. What we're trying to say is this: this is aluminium now. In this series, in this group 3 element, aluminium is the most abundant element in this series, and everybody knows what we use aluminium to do. We have some aluminium pots, we have some aluminium materials that we use at home. Even our electric wires, they are made of aluminium, because aluminium is very, very reactive as one of the properties of metals that we have talked about. Another one is this transition element and this actinide series. So we see that if you look at this, we're going to see iron, we see nickel, we see copper. So majority of all these elements, they are what we use at home. This is gold, they are what we use at home every day. See this silver, so we use them almost every day. So you can see why we need to study metals. Another one, they are all metals. Then we have some other things. So let us go to the physical properties of metals. We have talked about this one before, but just as a reminder, we need to just brush over it before we go to the business of the day. The first one is they are very, very strong. Metals are strong, like iron. Now iron is very, very strong. The iron is not something that you can just use your hand to tear it apart. No, it resists tear, doesn't tear like that. So they are very, very strong. They are malleable. Malleability means if you have a metal, you want to make them into a shape, you can just hammer them. If you beat them, they become flat. That is called malleability. Not all the elements can be done like that. It is only the metals that have that ability. Another one is ductility. Ductility means if you have a metal, no matter the shape of that metal, if you want to make it into wires, you can draw it without breaking, it will form like wire. That is ductility. Another one is sonorosity. Whether are sonorous, so if you hit them with something, they produce sound. That is called what is called sonorosity. They are shiny when polished. Yeah, metals are shiny. If you see sodium shines. They are very, very good conductors of heat and electricity. We have talked about that. In fact, we even talk about that quality. That is why they are being used as wires. I mean electric wires, electric transmission wires. They have high melting and boiling point. They have a very high melting and boiling point, something like gold around 1400 degrees Celsius. That is the melting point of gold. So gold metals are not substance that just decompose easily like that. No, they have high density. High density is just like if you have a small metal like that, it occupies a small volume and the mass is very, very great. So if you have calculate the density with respect to what you have in your hand, you're going to see that density is very, very great. When you have small amount and it weighs something around 100 gram per cent, you know that that substance is very, very dense. This is just the overview of physical properties of metal. Not all the metals possess all these properties. We need to be truthful. Like the first one that we said is very, very strong. It is, you can't sodium is not that strong like iron, because you can actually destroy sodium, but the thing is sodium remains sodium. But that is not business of the day. We are going to consider that later during the course. So let's go to chemical properties. That is just the start of the business of the day. The first one is the reaction with oxygen to form oxide. All metals react with oxygen to form oxide. So the way they react, the ease to which they react with oxygen are varies. That is what we are going to do when we are talking about reactivity series. So reaction with oxygen to form oxide, that is the basic things. Oxygen reacts with sodium, oxygen reacts with magnesium, oxygen reacts with aluminium to form the oxide of the respective metals that we're talking about. So I just use this X as hypothetical figure. It depends on the valency of the metals that we're talking about. If element is a monovalent element like sodium, so you need 2 atoms of sodium to react with oxygen to form sodium oxide, and sodium oxide is Na2O. That is for X equal to 2 because of 2 here. So if you have a calcium here, calcium X will be 1 here because calcium is a divalent element. So when calcium reacts with this one, even you are still going to have 2, but you will not have 2 here because calcium and oxygen, they have the same valence. So 2 equals 2, as we have talked about that before. Just brush over it if you are still confused. But the basic thing we just need to know here is the reaction of metal with oxygen. Metal oxides are bases. They neutralize acid forming salt and water. When we are talking about acid, we differentiated between acidic oxide, basic oxide, and neutral oxide, different from phosphoric oxide. So during that time we said metal oxides are basic because if you are dissolved in water, they form base. They form bases. That is why you see sodium oxide now. When they are dissolved in water, we have sodium hydroxide. When calcium oxide dissolved in water, we have calcium hydroxide. So metals form oxide that are bases. It is only the non-metal oxide that are acidic. Metals form positive ions when they react because they lose electrons. So that is one of the properties of metals. In fact, is peculiar to them. For the metals in the numbered groups like group 1, group 2, 3, 4, 5, all the metals that are there, I think metals stop on group 3. The charge on the ion is the same as the group number. What we are saying is this: if you have elements in group 1, that means the charge on that element is +1. If you have element on group 2, the charge on that element is +2. So, but when you go to the other group that are not numbered, like transition metals, like the antimonide and like lanthanide series, we can't use this for them because sometimes they exhibit what is called variable oxidation state. So they have variable valency, like we have in copper 1, you can have copper 2. When we have this proportionation reaction, that's when you have copper 1, but ordinarily copper is copper 2, but sometimes you have copper 1. So now let's now go to the reactivity of metal. That is the business of the day. Reactivity of the reactive element has a strong desire, a strong drive, a strong inclination. It is to form a compound so that its atoms gain stable outer shell. Let's explain this sentence. You have an element that readily releases electron, readily loses electron. We said that element is a very, very reactive element. We know that metals lose electron. So when you have in the group of metals now, when you now have one that can lose electron easily, that metal is more reactive than one that doesn't want to lose electrons. You can remember when we were talking about periodicity, we said the most reactive metal is francium because of the large size of the atom, so that there's not going to be any much effect from the nucleus to the outer shell. In such a way, francium can lose electron readily than sodium. Rubidium can lose electron readily than lithium, because lithium is closer, the atomic radius is close. But all in all, sodium is a very reactive element. Lithium is a very reactive element because they are metals. Metals are very, very reactive. But the ease at which they can lose electron dictates how reactive they are. Let's now take this reactivity one after the other, because the way elements react with some compounds varies. Number 1 is reaction with water. The sodium reacts violently with cold water. So in fact, if you put sodium atom onto the surface of water like this, you'll be thinking that the water is boiling because of the violent reaction to release oxygen. Not all the elements do like that. Like calcium now, the reaction is much slower than sodium. Magnesium, the reaction is much slower than calcium. So now if you now eat that magnesium, that is when you see vigorous reaction. So if you use a cold water now as a criteria for reactivity, you're going to see that sodium is more reactive than calcium, and calcium is more reactive than magnesium because of with ease at which they react with water. I don't need to delve into the concept of how elements react with one another. If we look at this table now, potassium reacts violently with cold water and it catches fire. So it forms hydrogen and solution of potassium hydroxide. Sodium reacts violently with cold water. Calcium reaction is less. Magnesium is less. Gold has no reaction. Silver has no reaction. What this one is trying to say is, gold is not reactive. Silver is not reactive. Copper is reactive, but far, far, far slower than what we can imagine. So these are now telling us how reactive all those elements are. So from the least, that is gold, to the most, that is the potassium. So only the first 3 produce hydroxides, others produce insoluble oxide. That is, even if they react at all, they produce insoluble oxides. Another one is reaction with hydrochloric acid. It is not safe to add sodium or potassium to acid in the lab because the reaction are explosively fast. So don't add sodium and potassium to hydrochloric acid in the lab because the reaction is fast, simply because sodium and potassium are very, very reactive. But other elements you can be tested safely because they are not as reactive as sodium and potassium. That's what we are trying to say. As usual, again, gold is not reactive, silver is not reactive. Copper there is no reaction. Even with concentrated acid, there is slow reaction in lead. So this one also show us the level, the order of reactivity. Reaction with metal oxides. You have metal oxide. Let's say you have magnesium oxide. So a metal will always reduce the oxide of a less reactive metal. You have a metal, a metal like magnesium, or like sodium, like calcium. You have another metal that is in oxide form. That's like zinc oxide, iron oxide, lead oxide. So when there's a reaction between lead oxide and sodium, there's going to be a decomposition between lead and oxygen. The sodium will take the oxygen from the lead because sodium is more reactive. The same way if you have zinc, iron and lead, or I mean zinc, iron or lead, if you have them and you have copper oxide, each of them will take the oxygen from the copper because they are more reactive. That's what we are trying to say. And again, if you have a solution of a metal and a less reactive metal in solution form, there's going to be exchange of ions like we said here now. So there's going to be free metal, the reactive metal in the solution. As in, what I'm trying to say is this: when you have copper carbonate, copper sulfate, and you have a sodium will take the carbonate or sulfate from the copper, then you have copper inside the solution. Carbon is more reactive than lead. That is, if you have carbon and you have lead oxide or zinc oxide or copper oxide, you have a carbon will take the oxygen from carbon dioxide. A metal displaces less reactive metal from solution. I've explained that one. This is the reactivity series in full. This is not the full element because somebody will be amazed, like, but it told us that we have every element in the periodic table, almost all of them are metals. Yes, this is not the complete table, but these are the most common ones that we encounter every day. So it is very good that if somebody, at least you know it offhand. I'm not saying you should cram something, but if you have been looking at it constantly, you should be able to know them offhand. Like sodium is higher than calcium is higher than magnesium is higher than aluminium. Then carbon is the surprise that is there. I am not saying this is electrochemical series, this is a reactivity series. So carbon is more reactive than zinc is more reactive than iron. So hydrogen is another surprise, but this place is very, very easy to memorize. Just know that hydrogen is more reactive than copper, and copper is better than silver and gold. Gold is the last, whether reactivity series or electrochemical series. And potassium and sodium are the most reactive. So metals above the blue line, carbon don't reduce their oxide because they are better than carbon, they are more reactive than carbon. So metals above the red line, they displace hydrogen from acid because they are more reactive than hydrogen. That is how it is. A top element displaces the below element. That is how it is. So some things to know about reactivity series. Let's just take them one after the other. The first one is the reactivity series is really a list of metals in order of is to form positive ions. Positive ion means the use of losing an electron. So if you want to know the reactivity of a metal, you test the metal by how much can it lose electron. If it loses electron readily, that means a very, very reactive metal. So the use to form a positive ion is the first thing. And don't forget that if they form positive ion, there is going to be stability. They form stable electron shell. So the more reactive the metal, the more stable its compound are. Yes, because it has lost the electron to gain that compound. The compound is stable, so they don't break. We are going to see later. They don't break. They are very, very stable. The more reactive the metal, the more difficult it is to extract from its ores. Yes, that is why if you want to extract sodium or potassium, they are being extracted by the most difficult method. That is electrolysis. You don't just see sodium like that in the earth crust. No, You see it from it ore that is being extracted by electrolysis. Because sodium is very, very reactive, if you expose it to air, it reacts violently. If you expose it to water, it reacts violently. So you can see that reactivity series is useful because we have used the reactivity series to explain the extracting of metals. The less reactive the metal, the less it likes to form compound. Yes, if you have a less reactive metals, you don't expect it to form compound. Example is gold. Gold in its natural form is gold. It doesn't react with anything. That is why if they want to extract gold, if they want to extract silver, if they want to extract copper, they extract them ordinarily like that from their ores. They don't react with anything. They are not in a compound form. Now let's talk about stability in relation to reactivity. Carbonate. Now let's take some compounds. If you have carbonate of some element, how will it affect them? Let's take sodium and copper as an example, because if you look at this now, this is sodium, this is copper. You can see that they are clearly different on the reactivities log. So now, if you eat sodium carbonate, what is going to be the effect? There's no change, because we said a very reactive element forms stable compound. They are not affected by it, but there's going to be decomposition here because they are not that stable. With hydroxide, there is no change also. This one changes because there is going to be evolution of water. What about nitrate? There is slight change. Sodium nitrate is fairly stable. There's nitrite, then there's oxygen. But in this case, not only copper, I mean other elements like silver, like even lead. So they form something like this. So we are just using copper as an example here. That is what we have on stability and reactivity. So we have explained reactivity with reaction of metals with water, the reaction of metal with HCl, then we have reactivity, that is heat, effect of heat and the reaction. So now let's go to general rule for thermal decomposition. Thermal decomposition is whether they will be decomposed or not. I mean stability. The lower a metal is in the reactivity series, the more readily its compound decomposes when heated. Yes, copper, you expect copper to be readily decomposed than lead. Lead to be readily decomposed, I mean lead compound, like carbon, like nitrate, lead decomposed than aluminium, aluminium than sodium. That is what we are trying to say here. So those elements that are very low on the reactivity series, they are easy to decompose than all those elements that are up high. So carbonates and hydroxides are very, very stable for sodium and potassium, but others, they are not stable. They form the oxide of the metal and CO2, that is even if they are carbonate. They form the oxide and water if they are hydroxide. What we are trying to say is this: if you have copper hydroxide now, it forms copper oxide and water. If you have copper carbonate, it forms copper oxide and CO2. That is on next decomposition. But sodium carbonate is stable, potassium carbonate is stable. Sodium hydroxide is stable, potassium hydroxide is stable. That is what we're trying to say. All nitrates are not stable. They decompose to the oxide of the element with NO2 and oxygen. It is only the nitrate of sodium and potassium that are stable. Not that the nitrates of sodium and potassium are almost stable like that. They form nitrite and oxygen, but they are fairly stable. They form sodium nitrite, though they are still a compound of nitrogen. I mean the nitrate of sodium or potassium. So this general rule, this apart from the first one that is common sense, all others 2, 3 and 4 you have to memorize them. That's carbonate, hydroxide of all the elements are not stable except that of sodium and potassium. Nitrates are not stable except that of potassium and sodium. Potassium and sodium nitrate they form nitrite, not that they decompose to oxygen, the metal oxide and the and NO2. No, they form nitrite and oxygen. Now, let us see if we can actually have any application for reactivity series. Number one is the termite process. In a railway line, when there is broken line on the railway line, so we want to fix it. Railway line is made of steel. How do we do it? So we have an oxide of iron, then we have aluminium. So when we put the two of them into that place where there is broken, that we want to join them together, then we put we put light there. When we light up the place, there's going to be a reaction between aluminium and iron oxide. Don't forget, aluminium is far higher than iron on the reactivity series. There's going to be exchange of atoms. That is when aluminium will take oxygen from this iron oxide. So when it takes the oxygen from the iron oxide, then it forms aluminium oxide. That one is stable to the atmosphere. Then this iron will remain. Then don't forget, there is heat. Then iron will be a liquid. Then it runs through that place where there is a breakage. When it runs there, it fools there. Then when it gets cold, it solidifies. That is, we have used that reactivity series to repair the damaged railway line. Making of a simple cell with copper and magnesium as electrodes. When you have a copper and magnesium as electrodes, you want to make a simple cell. You want the cell to light up a bulb. So just what we just need is to make a copper and magnesium electrode. You need any electrolyte is okay. Since magnesium is higher than copper in the electrochemical series, it loses electron than this. So when it loses electron, the electron will go from here. That is the negative electrode at the anode. The electron will go from magnesium through the wire into the copper. In that case, movement of electron constitutes what is called electric current. That is how to use reactivity series to construct a simple cell. So sacrificial protection of iron using zinc. So when you have iron, you are using it continuously, maybe in the atmosphere where there is water and oxygen. Sometimes later we are going to have something like a rust. When the iron will react with water and oxygen, it's going to be something like a rust, like a corrosion. In order to prevent that, you have zinc. When you have a zinc, you try to coat zinc on top of it. That is it. You can use electrode to do that also, and I've explained it during our discussion on electrolysis. Galvanizing is another way of sacrificial protection. You can use it to protect the pans, our roofings that we use to roof our houses. What we just need is you dip it inside the solution of zinc, in galvanizing, then you take it out. You are going to see zinc covering every place. You can use electrode also. That is electrolysis also. When you have the electrode of the copper you want to coat, you put it as cathode, then you use the water you want to use to coat. What I mean is this: you have an element A now, you want to coat it on B, then you make B to be a cathode, you make A to be an anode. So you make the solution, the electrolyte to be the solution of compound A. So compound A will be dissolving inside the solution. When it dissolves inside the solution, it is going to be gaining electron on the cathode of B. So B will be forced to give it electrode and electrons, and A will be on top of B. That is how to do it. Aluminum is able to protect itself through reaction with oxygen in the atmosphere. Yes, aluminum is reactive also, as we have said, because it's high up in the electrochemical series. It's reactive, but when you expose to the atmosphere, there's going to be reaction with oxygen. So when it reacts with oxygen, the oxygen coats the surface and prevents further reactivity. In such a way, aluminum oxide is formed and is able to protect itself from damage. So before we go, let us have some quick review of what we have learnt. These metals are sonorous, malleable and ductile, and again they are highly dense. Metals react with water, HCl and oxygen, and we have discussed that, and the activity shows the list of elements according to the ease of reaction. Then reactivity series is useful for some applications, as we have explained. I want to believe what we have learned is understood by us. So if that is the case, so let us meet next time on more discussion on metals and their compounds. Don't forget to share and like our video. Thanks for listening, and God bless you real good.